Hello, can you hear me?
Yes, we can.
Okay, then we will go ahead with the lesson. Done. So previously we talked about Advanced Encryption Standard, AES. And we used an online tool to test out our AES encryption. And now we need to study the modes of operation so that we understand what is this ECB, CBC, CFB, and OFB, and so on. So I will show you the following problem. Let's say you have at home a motion detector which sends the following message: motion when there is motion, or I would write like this: motion equals 1, like true when there is motion, and you have password. Okay, so, and since we don't want hackers to know whether there is motion at home or not, we want to encrypt this message because statistically, only dumb thieves go into a house that has people inside to steal stuff. Almost all thieves that want to steal something from your home, first they um, look at your home for maybe a week, maybe several weeks, maybe a month, and they mark the time when you leave home and when you come back, so that they approximately understand your behavior, your pattern of being at home, not being at home, and they only want to get into your home to steal your computer only when you are away. Because if they make a mistake, if they enter a house where there are actually people inside and the people panic, and if they happen to have some knives or some tools next to them, they can actually become aggressive and stab the thief, and then he's injured, or they engage in a fight and the thief accidentally kills the person, and instead of just stealing a 200 euro laptop, he now has to go to jail for first degree murder. Nobody wants it, so thieves want to make sure that the house that they want to go inside is totally empty. Therefore, they can do it in the following way. They can, for example, um, look at your house and see if you have lights on and if somebody is inside. But they could also, for example, an IT thief could try to use your motion detector information at home to check out if your motion detector says that motion is 1, it means somebody is at home and thief doesn't go in. But if it sends motion equals 0 for several times, then the thief knows that nobody is at home and they can easily enter and steal your stuff. And you might ask, well, what are these motion detectors? Well, for example, some security companies install wireless motion detectors because maybe the user doesn't want their interior to be filled with cables going from security remote control to every room. So they install, for example, wireless motion sensors. And these wireless motion sensors send this information. Or there are also these smart home devices, smart home motion sensor, which are, for example, connected to your lights, so that when you enter a room, lights automatically switch on, and when you exit the room, lights automatically switch off. And also, some of these smart home motion detectors are connected to your cell phone, and you can, for example, receive push notifications if the detector detects motion when you have set it, for example, in the away mode. So, you can use it as a security feature. So, but these motion detectors, they should send information encrypted, because thieves shouldn't know if there's, for example, nobody is at home for longer periods of time, right? Especially if, for example, you have motion detector in every room, and every room says motion equals 0. So thief knows that nobody is at home, right? So these motion detectors need to encrypt their messages. Let's check it out. And let's use a naive encryption. So we want the motion detector sends motion equals 0 when there's no motion. We use my secret password, we use advanced encryption standard, and we encrypt the message. And the ciphertext looks like this. So I can actually copy it, for example, in this. So this message is sent from motion detector to, for example, base station or to some internet or something like that. And hacker looks at it, and hacker has no idea what is encrypted. It's just all random hexadecimal numbers which are non-correlated with the input, right? And for example, when there is motion, then sensor sends motion equals to 1. It encrypts the message and it generates some other ciphertext. So let's check it out. For example, here. And this ciphertext is there is motion. You see, totally different from the one that says that there is motion, right? It's not just one bit different, it's everything's different, right? So let's say motion detector detects a motion because you move around your house and then you exit your house, and the motion detector reports that there hasn't been no motion for some time, right? So motion equals to 0. It encrypts the message, and now it sends to the base station that there is no motion. So next message is this. Then you come back home. The thief, who is sitting in his minivan parked next to your house, sees that you go home. And he also has some radio receiver. And when you go into the house, motion detector detects motion. Motion equals to 1. It encrypts the message and sends out this ciphertext to the base station and to your cell phone saying, hey, I detected motion. Okay. And check this out. The message that there is motion. Oh, sorry, this is no motion, for example. I'll just write it. No motion. And yes motion. And this is no motion. And this is yes motion. Okay, so when there's no motion, sensor sends this ciphertext. When there is motion, it sends this ciphertext. When there's no motion, it sends this ciphertext, which, as you can see, is the same as no motion ciphertext previously. And when thief sees that there is motion, thief also sees that this ciphertext is sent, which is the same as the other ciphertext, which was sent when there was motion. So basically, even though the contents of the messages are encrypted, every time there is motion, the same ciphertext is sent out. And every time there is no motion, the same second ciphertext is sent out. And thief doesn't even have to know whether the message is motion equals 1 or motion equals yes. Every time there is motion, he sees one ciphertext, this one, and when there is no motion, it sees the second ciphertext, this one. This is again side channel attack, where when something happens, the same ciphertext is sent out. Thief doesn't need to know what's inside. He just sees if motion detector sends this second type of ciphertext every time, thief knows that everybody is away from house, the house is empty, and he can enter. And on the other hand, if he receives this ciphertext, then he knows, okay, somebody is at home, I don't go inside the house. So actually, even though we have encrypted all messages, actually, we also have leaked information about our home vacancy to the thief, because every time there's nobody at home, one ciphertext is sent, and every time there is somebody at home, the second ciphertext is sent. So this is a side channel attack. And so even though encryption algorithm itself is extremely strong, is impossible to guess the password, well, we're using it in a weak way. And so we need to come up with some algorithms that would actually make this communication secure. Okay, so so let's see how we can do it. And we can do it with something that is called modes of operation in block cipher. Block cipher modes of operation. So I will show you a wonderful picture from Wikipedia. Block cipher mode of operation. Check it out. So if we are using this simple method of encryption where we just use the same plaintext, the same password, look at these pictures. So original image is a penguin, but when we encrypt all white areas, they result in the same pattern of gray areas. When we encrypt black, it results in this the same little bit different gray area. These yellow parts are also encrypted to the same pattern. So even though we have encrypted the picture with the strongest encryption method possible, advanced encryption standard, the image can still be recognized. We can still see that there's a penguin inside this picture. And if there was some text or some secret message, we would be able to see that secret message if it is in the picture. And therefore, advanced encryption standard alone isn't really the full answer to encryption. You also need to use some of the modes of operation which are not electronic codebook. And here's the idea. The idea is that when we encrypt the message, we should somehow make sure that every time we have the same plaintext, different ciphertext is generated, right? So different ciphertext. So we encrypt a block of white color and we get some gray, something gray. Then when we take the next chunk of white color, we should get a different result. But unfortunately, since input is the same and key is the same, we cannot get a different result. So one mode of operation is called cipher block chaining. And the idea is the following. We have plain text. Right now, we just ignore this initialization vector. Let's say that it's nothing, it's 0. So we have plain text. Then we encrypt the plain text and we get ciphertext. So this was white color. We encrypt it and we get some kind of gray color. But now we take the output of this encryption and we XOR it with the next block, which is white. But since we XOR it with gray, white XOR gray will be some different kind of gray. Then we encrypt it, and since the input was different from the previous input, the output will also be different. And even though we had two white colors as input, since the second white color was XORed with previous gray color, the result will be different. This different result will be then XORed with the next block, which will result in even another different color. As a result, by chaining ciphertext XOR next plaintext XOR next plaintext and so on, we make sure that even though inputs are the same, outputs keep changing. Okay, so this is called cipher block chaining mode of operation. Cipher block chaining. So I will show it to you with an example. For example, like this. Motion equal 1. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So as you can see, well, I generated some maybe silly message, but the idea is the following. Our message has 32 bytes, which have the same input, motion equals 1, 8 spaces, motion equals 1, 8 spaces. The cipher takes first 16 bytes, it encrypts, and it gets this output. Then it takes next 16 bytes, and since they are the same, the output is also the same. As you can see, both chunks of information got encrypted to the same output, and the hacker sees that first 16 bytes and second 16 bytes is the same thing. So for example, if instead of this text there was white color, it would produce the same gray color. And the hacker sees, okay, these fields are the same. He doesn't know the color, but he can still repaint the picture in different colors and still see approximately what is inside of the picture. And if it's, for example, some bad picture or something like that. Now, if we use mode cipher block chaining, and let's say initialization vector is just all zeros, so we don't really care initially. So if I click encrypt now, the first block, the result is the same. So encryption of this part results in the same output. But the next part is this ciphertext XORed with the next block of message and then encrypted. As a result, the output of the second part is totally different bits compared to the first part. So this is a method, as a basic principle method, to encrypt the same plaintext to different ciphertext. Okay. So for example, if you have movie, you can encrypt it this way, and hacker or some pirate who is pirating the movies and putting them in torrents, he cannot watch your movie because you're using encryption, which even for the same frames produces different ciphertext. Okay, so let's see. Maybe it doesn't allow me to have two windows in the same browser. So I just copy this. I will put it here. And let's see how the decryption works. So AES, I click decrypt. And as you can see, the output is decrypted correctly. Motion equals 1, motion equals 1. Let's look at decryption now. So to decrypt, we first take the ciphertext, calculate decryption, and get the plain text. And then we take the same ciphertext, we decrypt the next chunk of ciphertext. The output is XORed with the previous ciphertext, and we get plain text. So basically, we're just doing the same encryption, just observe to do it in the correct order. So this ciphertext is used to get plain text and also to XOR next ciphertext decryption to get plain text, right? And maybe you don't have to overly worry about it, because encryption libraries do this thing automatically. You just need to know that you must set the library to work in, for example, Cipher blockchaining mode, because by default, all libraries use electronic codebook, which is this unsecure way of encrypting messages. Okay, so right now this algorithm lets us produce, for example, this third picture is how the result looks if you use, for example, Cipher block chaining. So since the next block is based on previous block's ciphertext, everything is just totally random. It's impossible to see anything here. You cannot see a penguin in this picture because it's all randomized. It really looks like pseudo-random output. And actually, advanced encryption standard is so strong that you can use it as a random number generator, as pseudo-random number generator. If it wasn't, then it would be a weak encryption method. But you just take some value, encrypt it, then take the output, encrypt it again, then take the output, encrypt it again, and you continue it, and you get all of these random ones and zeros, which actually can be used to generate random numbers. Okay, so this is one method to generate random numbers. Okay, so this Cipher blockchaining is, a good thing, but it's not the only way to encrypt and decrypt securely. There are actually several other methods of modes of operation. Let's see. Next one is propagating cipher blockchaining. So basically what it does is it takes plain text and ciphertext and XORs both of them, and then XOR them with the plain text, and then encrypt, and then the output is XORed with plain text, and then XORed with the next plain text, and so on. Why would it be necessary? Maybe there is a reason, but generally I don't really see a reason, compared to the previous one. But it's just possible to use it. So this method is not really widely common. It is used in some encryption algorithms, but not much increase. So next mode of operation is Cipher Feedback, and this is an interesting one. So okay, this is an interesting one, and we will now introduce ourselves with a concept which is called initialization vector. So here is the idea. Even if we are using this Cipher block chaining, if we have the same plain text, it will produce the same ciphertext. It will forward the same ciphertext to next plain text. So generally, encrypting the same message with the same content will anyway produce the same ciphertext. So it is visible here. If I set back motion equal to 1, oops, where is it? Okay, so this is my secret password. It's all zeros. The input is plain text motion equals 1. Motion equals 1. Advanced encryption standard, cipher block chaining. So if I encrypt, every time I encrypt, I still get the same output. So we will now introduce something called initialization vector, or mostly it is just simple counter, and it is sent together with ciphertext, and it is used as a counter to make sure that even if we have the same plain text, we get a different result every time. So the idea is the following. The person that encrypts data first comes up with initialization vector, which is, for example, packet counter. So this is packet 0. Initially, it's all zeros. And then, instead of encrypting plain text, the person encrypts initialization vector using the secret key, and then the output is pseudo random ones and zeros, which are XORed with plain text, and you get ciphertext. You might see, oh, plain text is on the opposite side of the encryption, but it doesn't matter because it's XORed with something that you can only generate if you know the key. So initialization vector can even be sent together with ciphertext, but hacker, knowing ciphertext and initialization vector, cannot really do anything with this information to decode the messages because he doesn't know the key. So initialization vector is encrypted. We get some ones and zeros, XOR with the plain text, and we get ciphertext. And then the result is fed into next block, encrypted, XORed with plain text, and we get ciphertext, and so on and so on. And as I previously said, since this block cipher is strong and generates almost random ones and zeros, XORing plain text with random ones and zeros makes a 50% chance for each bit to be flipped. As a result, this output is unreadable. It's impossible to see what's written in there because half of the bits are flipped and half are not flipped, and location of flipped bits is totally random, and you cannot read the message. Okay, but the catch is that initialization vector is something that we called a nonce. Nonce, also written in small letters, is a number used only once. So it can be public, but it must be used only once. And every time you send a message, you increment it. Okay, so you send a message, you increment initialization vector. For example, just add 1 to it. And you do it after every message. And you also store the incremented value in non-volatile hard disk memory. Non-volatile means permanent, or, something like hard disk. So you increment it and you store new value in non-volatile memory so that even after reset, it is not lost and you don't start from 0 again. So that you make sure that you only use each of its values once. So initialization vector is the same length as block cipher. So in our case, it is 16 bytes long. So in wireless sensor networks, in the lifetime of the device, you cannot go through all of the combinations because 2 to the power of 16 times 8, 2 to the power of 128 is this many messages. And wireless sensors don't send so many messages in millions of years. So in embedded systems, you don't really have to worry about it, right? However, in computer networks, when you download movies, watch torrents and YouTube, then amount of data is so great that sometimes this initialization vector reaches its maximum and rolls over to 0. And in those cases, people just need to change the key. They need to change the key and then start new initialization vector from 0 with a new key so that there is change. Otherwise, this is not secure. But generally, you send a message, you increment this initialization vector so that next time you encrypt a different number, XOR, and you get different ciphertext. Let's check it out through this example. So at the beginning, initialization vector is 0. I encrypt, I get this given ciphertext, okay? If I use the same initialization vector again and I encrypt, well, guess what? I got the same ciphertext, so hacker knows that I sent the same message. However, if I implement the algorithm correctly, and if I increment initialization vector every time, look what happens after it is done calculating. So I change initialization vector to 1. I hope it works. Let's see. Calculates encryption. I don't know why it is 256 bits. But let's see. Let's look at this area. Will it change the output? Well, this web page sometimes gets really slow. I don't know, maybe it's mining bitcoins in the background. That's why it's free. Maybe all these advertisements just eat up all of the resources of the computer. Okay, it encrypted. And as you can see, even though we had the same input, the same password, because we changed the initialization vector, this counter, we send a message and we increment it by 1, as you can see, the result is totally different. I'll just write it down in this notepad. So, sorry, in this paint. The message sent, the second message looks like this. So we send it and we increment it to 2. And now I will encrypt it again. And let's see what happens. So it's 54, 21, 44, F7, 9D, 32, and so on. Let's see, it will calculate it at some point. Actually, computer calculates this thing very quickly. I just think that this web page is just so full of JavaScripts running advertisements and something else that it basically just hangs the whole browser and doesn't do what it's supposed to do. It should just encrypt it. So I don't know. Okay, while it's calculating, I'll just write you what happens when we send the message. So when message is sent together with the ciphertext, you also send initialization vector 0, 0. I don't know which would it be. 0, 0, 0, 0. What the hell? 0, 0, 0, 0, 0, 0, 0, 0. Actually, I can just copy these because they are 16 bits. Copy and paste. And the last one was, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is our initialization vector value, which is sent together with the message. Okay, it finished calculating. Check this out. Initialization vector is 2 and zeros in front of it. And the ciphertext is this. And let's check out if it's different from the previous one. So I'll just paste it here. And yes, it's different. So even though we encrypt the same message, because we change the counter, every time, the message contents change. The ciphertext contents change. So like this is true. Okay, so what is sent out to the receiver is this initialization vector value, the ciphertext first block, and the ciphertext second block. Next time, even though we have totally the same message, we have different initialization vector. As a result, ciphertext looks totally different. And now, if we change the counter to 3 and we also change the message to, for example, motion equals to 0, let's see what is going on in this page. La la la. I wonder if there are some scripts running. Probably yes. Okay, so I changed the message to motion equals 0, and I increment the initialization vector, and I do the encryption. And let's see what the result will be. And as you can see, this initialization vector can also be used with Cipher block chaining. So Cipher block chaining is here. Plaintext is XORed with initialization vector, encrypted, and the ciphertext is produced. So the Cipher feedback is similar, but you can observe the following thing. You take the initialization vector that you receive with the ciphertext, you encrypt it, then you XOR it with plaintext, and you get ciphertext. To get plaintext back from ciphertext, you don't need to do the decryption. You can take the initialization vector, encrypt it, XOR it with ciphertext, and you get back plain text. As a result, this encryption method can only use the encryption part of the cipher, and you can even save money by not implementing decryption at all. You can just make a 2 times cheaper, 2 times more simple chip, which only does encryption. And in this method, since the encryption happens by encrypting the counter and the ciphertext XOR'd with plain text, you get the final ciphertext. The decryption happens using encryption of initialization vector again. Okay, so here is the block diagram, and you can actually use much simpler method. So let's see, it's still calculating. Okay. There is also this output feedback, where you take the input, encrypt, XOR with ciphertext. Basically, I don't even know if there is difference between this and the previous one. Looks the same to me. Encryption, plaintext XOR ciphertext, encrypt, plaintext. I don't see the difference here, but fine. And the next mode of operation, which is very similar again, well, basically they all have in common this counter, but this counter mode is even more interesting. Check it out here. So you take this initialization vector, which is here called nonce, and then you evaluate how many bits, how many blocks will be the length of the message. And let's say the maximum length of message is, for example, 1 megabyte. So bottom, okay, 1 megabyte is a little bit too much. Let's say the maximum length of message is, for example, 4 blocks. Okay. Oh, actually, 1 megabyte isn't that bad. Okay, let's say it's 1 megabyte. 1 megabyte means that you dedicate bottom 20 bits for a counter, and top 20 bits is this initialization vector. And instead of incrementing it by 1, you increment it at this 20th bit position. So these are 8, 16, this is 24 bits. So basically you start incrementing at, for example, higher location. So this is our initialization vector. And in counter mode, this would be 0. And you increment, for example, bit number this. This would go to 1, to 2, to 3. This bit and everything ahead is incremented by 1 every time a new message is sent. And this bottom part is incremented within 1 transfer on each block. So right here, first block of multi-block message is encrypted with counter equal to 0. Next block is encrypted with counter equal to 1. Next with counter equal to 2, and so on. Then you send the message and you increase only the top part for the next message encryption. And on receiver side, the receiver takes the nonce that you sent it, encrypts, XORs with ciphertext get plain text. Next part, it only increments the bottom counterpart of the initialization vector, encrypts, XORs, gets plain text, and so on and so on. And this encryption method has the positive property that you can put several encryption blocks in parallel, and you can calculate the result much faster because you can parallelize these encryptions and decryptions. You can do several blocks at the same time because nonce is the same. You just increment counter on each of these sub parts, and you get results in parallel at the same time. So your encryption and decryption can happen much faster. So let's say you are downloading a movie. Movie is several gigabytes. Each part is encrypted. Each 16 bytes are encrypted. So if you would do it in a regular way, you would just take a nonce, encrypt, calculate XOR with ciphertext, get plaintext, then you increase the counter of blocks, encrypt, and get plaintext, then increment counter, encrypt, get plaintext, and so on. But if you, for example, could have a CPU that has, for example, 8 such blocks in parallel, you could encrypt or decrypt 8 blocks at the same time. And your processor would be able to run much faster on encrypted data. Let's compare it to the previous methods of encryption. So for example, this output feedback. Here, you encrypt the initialization vector, XOR, and then encrypt the next block. For decryption, you cannot decrypt the next block until you have calculated the previous block. So this method cannot be parallelized. Um, so run in parallel, maybe is better word. So this method, before you encrypt the next block, you wait for the previous. For the third block, you wait until you calculate the second block, and so on and so on. And so this is not perfect. It's good. It runs on single core processor, for example, but you know, modern computers have, for example, 8 cores, right? I don't know. Most computers have 4 cores. Many have 6, 8. You can buy with 18 cores. I think the newest Macintosh computers, you can also buy some Xeon processors with 44 cores. And if each core has an encryption decryption block, you could run up to 44 encryptions or decryptions in parallel, and they would happen blazingly fast. Let's say that you have 8 processors in parallel. It means that instead of, for example, 8 seconds, decryption takes only 1 second, and that's a big difference, right? So this counter mode has a very good property. And even if you have a single core processor or a microcontroller, well, it can still calculate the result. It just takes the first block, decrypts, increments counter, takes the second block, decrypts, increments the counter, and so on. So it doesn't make single core processes to run slower, but multi-core processes will definitely benefit from this. And basically, these are all modes of operation, and several modes of feedback, and several modes of counters and initialization vectors, and so on. So now what you need to remember is some of these algorithms, even if used in these block cipher modes, can still be implemented in the wrong way, and they still can have problems. Oh yes, and here's a very good thing. So this electronic codebook mode of encryption, the reason why it's not secure is called replay attacks. So you take an old message, send it again, since they were encrypted to the same ciphertext every time. The receiver doesn't know that it's an old message, and it just uses it. So these are prone to replay attacks. These cipher blockchaining and everything else where you have initialization vector, vector increments every time. It's stored on both ends. It's stored inside the sender and receiver. So all the messages would be rejected anyway, because the initialization vector is old, so it will be rejected. Of course, it can happen that you can, for example, steal some message that wasn't received by receiver and then replay it again. So this nonce should also have a timestamp, right? But this will be a little bit different topic. Right now, this just makes sure that every time you send a new message, the ciphertext looks totally different, even if the message was the same. So as you can see, this thing has finished calculating, and we changed the message. We incremented initialization vector, and now the output is again totally different from the output that we got previously. And hacker, since every time the output is different, hacker has no idea whether this ciphertext is on the same message or a different message, because counter is incremented every time. And so in this web page, it initially works good, and then it starts to work really slowly. But generally, you can just test out different modes of operation: cipher block chaining, cipher feedback, output feedback, and so on. It doesn't have counter mode, but you can test counter mode maybe in some different web page. Okay, so here is, I don't know, probably the best encryption method, counter. And now, to make sure that the things that I'm telling you aren't complete balonies, let's go and check out what is the latest version of internet security using. So let's see, TLS, I think. So there is this standard called transport layer security, which is the encryption method for internet communication. So basically, it is used by, it's used by just web browsers and everything that happens on the internet. Let's see, transport layer security. The old version was called Secure Sockets Layer, SSL. Sometimes the name is still used, but the correct modern version is TLS. It's a set of cryptographic protocols designed to provide communication security over a computer network. So in reality, it's just TLS is the protocol that is used to encrypt web pages, to connect to remote servers, to send, I don't know, emails, and so on, to connect to FTP. So this TLS is the one that is used. These protocols are open, they are well defined, anyone can go and read them, and their security lies not within the secrecy of how it works inside, but quite contrary, it depends on the key, on the password, and not on the algorithm. The algorithm is totally welcome to be broken so that it could be improved, right? And let's just check out what underlying encryption methods are used in TLS. So as you can see right here, so how it involved. So SSL was, I don't know, a long time ago. It was somewhat unofficial. Then SSL 2.0 was standardized. SSL 3.0, TLS 1, 1.1, 1.2, 1.3. So this TLS 1.3 is the active version right now. And let's check it out. So if I recall correctly, something like TLS 1.0 had this problem that when you connect with the wrong password, it checks the first part. If it's wrong, then it sends back immediately that it's wrong. If it checks the next part, if the first part was correct and it checks next part and next part is wrong, then it sends reply a little bit later. So you could kind of catch how far you are correct, and the hackers could actually beat this security within something like 10 minutes or something like that. So yeah, this is why these protocols are constantly updated, and most of the time servers oftentimes have automatic updates built in, so that as soon as a vulnerability is detected, uh, the server, the website programmers receive some information about it, and they can correct it, or they receive automatic updates by the creators of this server uh, software, and so they're fixed, and this TLS version is incremented. And let's check out so what algorithms are used. And so these are key exchange algorithms that will be a little bit later, but the cipher. So as you can see, AES has several versions: GCM, CCM, this is counter mode. CBC is cipher block chaining, and other encryption standards also were used before AES. And basically, if we look at the block ciphers with mode of operation, then in latest TLS 1.3, basically only AES encryption is used, and either it's used with Galois counter mode or with a simple counter mode. So CCM, counter with cipher block chaining message authentication code. So CBC MAC. This thing not only has a counter, but it also produces message authentication code. So changes in the ciphertext could also be detected, right? But I'll tell you about it a little bit later. Let's just check out this thing. So basically, basically the only AES mode of operation used today in TLS protocols is AES counter mode, exactly because it provides all the benefits that previous modes offered, but also it can be run in parallel. So if you have multi-core processor, each core can decrypt part of the message at the same time, and you get the result faster, right? So as we can see, I'm not lying to you, AES is a real algorithm. It is used in real modern systems right here, and it's deemed secure. And as you can see, I'll put it like this. So as you can see, there were older modes of operation, for example, RC2, DES, and others. And initially, they were used, but as the time went on, either their passwords were too short, so they got marked as insecure, or maybe somebody found some vulnerability there, or sometimes, uh, for example, this area GCM, maybe it doesn't even have a vulnerability. It's just that algorithm is a bit slower than AES. So yes, maybe this ARIA GCM mode is good and secure and nobody has broken it, but maybe it just takes 2 times longer to encrypt or decrypt. And because of that, since AES is, for example, 2 times faster and provides the same security, this ARIA is just, just thrown away without real reason, right? And as a result, since TLS 1.3 only supports the last 2 standing protocols, it's much easier to implement TLS in the processors, because the problem with the older systems was there were so many algorithms for encryption, and the operating system had to support all of them, because, for example, I don't know, a laptop connects to the server. The laptop only supports seed CBC, so the server needs to support it. And another laptop has AES CBC, so the server needs to implement this as well. And so the server has to know all of these algorithms in case somebody connects exactly with that one algorithm. So there was a lot of overhead in server and computer networks because there are so many options to encrypt. So now in the latest version, they just decided, let's just use one mode, which is AES GCM or AES CCM, and that's it, right? And these algorithms can easily be also run in embedded systems, in small microcontrollers. So small microcontrollers are just as capable of security as big desktop computers, which is actually a really, really good thing. And these are block ciphers. There's also this field of ciphers which are called stream ciphers, and they have different internal workings. I don't know, we can just check this out. Salsa 20, for example, is an stream cipher, and the idea is that it doesn't work on blocks of, for example, 16 bytes, but it just generates one bit every time you ask it. You say, give me one random bit, and it gives you one random bit based on the password, the key, and on the previous bit, right? So basically, it just generates pseudo-random stream of ones and zeros. And as you can see, Cha-Cha 7 has complexity is something 2 to the power of 248, which is great. And these algorithms exist. But the problem with these algorithms is that most embedded systems don't have them built in. AES is kind of easier to implement, more common, so most people just use AES, and if they only want to send 1 byte, they just have to add 15 zeros at the end and then encrypt and then send. So stream ciphers are not very kind of that much mainstream. Maybe they are in servers, but in embedded systems, they are not very popular. In embedded systems, everybody uses block ciphers with AES, okay? So, and the thing is that block cipher can also be modified to become stream cipher. You just come up with a key, and then you just take the counter and encrypt it, increment by 1, encrypt, increment by 1, encrypt, increment by 1, and you will get random ones and zeros out of this block cipher. So it's possible to use it. Just never use the same initialization vector, always increment it, always save it. So between resets, it is not used again. Okay, so that's about block ciphers. And now let's check out several things. First one is web. So when the first wireless routers appeared, people realized, wait a minute, my router and my laptop are sending my private data to all directions with no encryption. So when I connect to a website, everybody sees to which website I'm connecting, because initially the same messages that were sent over wire were sent over air. So people quickly realized, wait a minute, if I don't want everybody to know what internet websites I'm browsing, we need to encrypt the wireless communication. The Wi-Fi needs to be encrypted. So they came up with this wired equivalent privacy algorithm, which was, you know, decent for a couple of months. And then it turned out it was full of weaknesses. And let's check out what weaknesses were inside of these routers. So first of all, weak security. So RC4 was the encryption algorithm that was used inside. it is a stream cipher, so the same traffic key must never be used twice. As a result, it also had initialization vector. But guess what? The initialization vector of this web was only 24 bits. 24 bits. Let's check out. 2 to the power of 24. Is this let's see, how much is this? Let's say that each of these initialization vectors is used, for example, for 16 bytes. So I multiply it with 16 bytes, for example, just as an example. Then I divide it by 1024. This is the kilobytes, and divided by 1024. Basically, after 256 megabytes of information, this initialization vector overflows, rolls over, and while you are downloading a movie, this initialization vector has rolled over several times, maybe several hundred times. Check it out. For a 24-bit initialization vector, there is a 50% probability the same IV will be repeated after just 5,000 packets. And it will definitely be exhausted after just 2 million packets, which is the size of a decent movie, right? So while you're downloading movie, this initialization vector rolls over, it's used again, and if hacker detects that it's the same initialization vector, then he can XOR old plaintext, old ciphertext with new ciphertext, and he can actually get the part that came before initialization vector, and he can retrieve the plaintext this way. This is why initialization vectors must never be used twice. It is called two ciphertexts attack. So if you take this part twice and encrypt on two different plaintexts, you XOR the ciphertext and you get the XOR of two plaintexts. And after some accumulation of data, you can actually easily get the plaintext. You don't even have to guess the key. These known ciphertext attacks, they don't need key. They can just XOR the outputs and get the plaintext XORs and so on. So without even knowing the password, it's possible to reverse calculate the plaintexts and get the websites that you're visiting and so on. So first mistake of this algorithm was that it had only very small 24-bit initialization vector. Modern initialization vectors are how long? 128 bits, right? So 2 to the power of 128 is this much. How many gigabytes is it? So let's say this is used on 16 bytes. So we multiply it by 16, and then we divide it by 1024. This is the kilobytes, divided by 1024. This is megabytes. 1024. This is gigabytes, divided by 1024. This is terabytes. So using 128 bit long initialization vector, you can encrypt this many terabytes of information until the initialization vector is exhausted. So for example, I don't know, since your computer maybe never overflows in this number, maybe Facebook server overflows because millions of people connect every day, thousands of times, download a lot of movies, and then of course their counter exhausts and they just generate a new password. And maybe they use, for example, 256 key passwords. But anyway, it's a huge, enormous, large amount of data. So that's the first mistake. And the second mistake, which is really funny, is every time the router lost power and was switched on again, the initialization vector fell back to 0. So again, it was used the second time, and hacker could catch this and get all the same initialization vector encryptions and get the plain texts, right? So it turned out to be absolutely weak. But, you know, it was the first protocol, so only those who don't do anything make no mistakes. So, and then they actually found some other weaknesses, and to the extent that, for example, the latest was that um, when you catch something like 40,000 packets, there's a 50% probability that you are able to get the password of your network router, the key, right? And 40,000, you know, movie is several gigabytes, so that would be maybe millions of packets. So while you're downloading a movie, your password has been stolen several times, right? So not secure. And of course, everybody knew about it. And here was the problem. The first routers were very simple and remote updates were mostly not possible. So, you know, knowing these problems, they could be fixed in software, for example, by using longer passwords. But since many routers didn't have remote update, they couldn't be updated and these changes couldn't be implemented. So the best thing to do was to just throw your old router in the trash and buy a new one with WPA or WPA2 security. And the newest routers usually have a possibility to update them. So for example, I can connect to my Wi-Fi router right now, except I don't remember the password. But if I log in, there is also a button to update. So I have MikroTik router. It's a Latvian company that makes routers, very good company. And they publish updates on their website, and the router, if you log into it and you click a button, the router connects to MikroTik's server and installs latest updates on itself. So even if MikroTik made some small mistake in security, or maybe the algorithms were detected to have flaws, they can be updated. You don't have to throw your router in the trash just because somebody found some small bug in the security algorithms. You can just update it to the newest version, which is a really, really good thing. Modern technology actually saves the planet from waste and trash. Okay, so in web, I think they started to use advanced encryption standard, first of all, and then they also started to use different things. So WPA2, let's see. So some of them use advanced encryption standard. Yeah, actually the newest version, WPA, uses advanced encryption standard. The old web and WPA used RC4 stream cipher, which is not considered that much secure anymore. So RC4 stream cipher, it's very simple. Multiple vulnerabilities have been discovered, so it's considered insecure. Okay, and the last thing that I want to show you is the following. So when you develop your system, and let's say you're making a wireless system using microcontrollers and you want it to be secure. Well, first of all, what you can do, you can take a microcontroller and you can also find AES library in C programming language. Somebody took the description of advanced encryption standard text and wrote it into a code. So here is a code which does the encryption. So for example, I can download it from the internet. So this code has the S box. It also has round key S box. This is used for password expansion. and basically you give it the block you want to encrypt, and it just mechanically does all of the stuff, like expands keys, then it mixes the columns, substitutes bytes, shifts rows, mixes columns, and so on. So basically, there is a software which can calculate it. However, as you can see from the number of lines, this code is pretty long. It is, for example, almost 600 lines, and there are many loops, as you can see, for AES backlog, blah, blah, blah. So several things are done several times. So if AES is run in software, it's not very fast. You can calculate it in software, no problem, but it's just, it's a lot of action. But knowing that encryption is really important, people have started to build encryption, for example, AES, as a hardware accelerated block inside the microcontrollers, because this can be easily done in hardware because the process is really just, simple. Replacement can be done using lookup table read-only memory, mixing, shifting rows and mixing columns can be done by simply rerouting the wires to the next part of flip-flops and so on. So this can easily be implemented in hardware. As a result, many companies sell microcontrollers that have advanced encryption standard engine built in. I don't know, for example, Silicon Labs. Let's check out. So products, microcontrollers, 32-bit microcontrollers, I don't know, Happy Gecko, decent microcontroller. And if we go to its datasheet, it says right here, wait a minute. Let's search. Hardware cryptography, advanced encryption standard. So this AES supports up to supports exactly 128-bit keys, and it calculates them the result. It encrypts and decrypts in just 54 cycles. Trust me, the code that we found here, it would take thousands of cycles to calculate the encryption and decryption by hand, whereas when it's implemented in hardware, it takes only 54 cycles to do encryption and decryption. So hardware accelerated advanced encryption standard is of course much faster. So if your microcontroller, if you want to take the cheapest microcontroller that you can find, it will not have advanced encryption standard hardware acceleration built in, but you can use code. But if you want your chip to be more power efficient and calculate advanced encryption standard encryption faster, you would buy a chip with AES built in. And many companies, for example, ST, pretty popular microcontroller manufacturer. Let's see, microcontrollers, microprocessors, blah, blah, blah. For example, ultra low power microcontrollers, STM32L4. Maybe they will have some information about them. Okay, or L0. L0, 0. So many of these processors that ST produces, they have two options. So here you can see, you can buy the same chip with or without encryption. So black ones are with 128-bit AES hardware encryption, and you can buy a model without encryption. And of course, encryption engine costs money. It takes some space in the silicon. So these light blue chips will be maybe 20 cents cheaper. And if you definitely need hardware encryption, you can buy with hardware encryption built in, They will be a little bit more expensive, but they will definitely be really, really fast in encrypting and decrypting data. And also, these hardware encryption and decryption engines are usually better than software more prone to side channel attacks, because sometimes this code will optimize some places and make some things happen faster, some things happen slower, and people can measure the speed of encryption and decryption and determine maybe some part of the plain text. But these hardware accelerators, they work at fixed speed of, for example, 54 cycles, and it doesn't matter how many ones and zeros are in the plain text or ciphertext or password, it always takes 54 cycles. So you cannot measure time and determine anything about it. Just most important thing that the power consumption doesn't change. That's what they have to do. So you can buy them. And now let's look at the final take on hardware accelerated AES. Let's go to CPU bus and compare two CPUs. One of them will be T4200 and the other one will be, for example, 4870HQ. So this Intel Pentium T4200 is the processor of my previous laptop, which I bought in year 2011. So it's almost 10 years old laptop, which still works. And this is its processor. It's dual core processor, core 2 duo. And this 4870HQ is the processor of my current computer. And let's compare them. So if you check out their speeds, my previous processor had only 2 gigahertz, and this new processor has 2.5 gigahertz. So actually the difference isn't that big. So we would assume that, so for example, 2 over 2.5, so the new one is just 1.25 times faster than the old one. So I would see 25% increase in performance. So for example, something that took 1.25 seconds will now take only 1 second to happen. Let's check out if it's true. And actually, this one is in 2009 and this one is in 2014. And let's check out. However, if you look at encryption speeds, my new processor is gajillion times faster than the old processor. Let's check it out. It should be only 25% increase in encryption speed. However, if we calculate these numbers, 4400000 divided by 84600, so my new computer calculates AES 52 times faster. So what took my old computer 52 seconds, this new computer can do in 1 second, much, much faster. And here's the reason why. The old computer did not have advanced encryption standard built in, right? So actually, when browsing internet, it would consume a lot of electricity and also browse the website slowly, because all modern websites are encrypted. As a result, if I just want to read this data sheet, first it's downloaded, then it's decrypted. My previous computer had to do it with the code, for example, similar to this. So it needed to do all the encryption, decryption by hand. The new processor has advanced encryption standard acceleration built in, because around year 2010 and a little bit later, advanced encryption standard became really mainstream and the only one that's used in, for example, TLS 1.3. So the CPU manufacturers started to implement and implant AES encryption engine inside the CPU, as a result, this new processor can encrypt data 52 times faster simply because it has this advanced encryption standard hardware accelerator built in, right? So this is the difference between new and old processors. Actually, all processors are the same speed, around 2 gigahertz. It's just what kind of acceleration engines are built in. And the more expensive the processor and the newer the processor, the more it has built in, automated. So as a result, it just works much faster. Okay, so I guess that's all for today about encryption and about modes of operation. So if you have some questions, you can ask them. If not, then this is all for today.